You deleted the row. A customer asked you to, in writing, and you kept the ticket that proves it. The delete returns success in 4 milliseconds. A full 9 days later, that row is back in production, served to anyone who asks, exactly as it was before you removed it. Nothing failed. No alert fired. No log line anywhere says a row was restored. Something you wrote simply stopped being true. The bill for that lands on you, and it is a painful one. You told a person their data was gone. You were wrong, and you were wrong in writing. The hours you lose tracing its return are not the expensive part. The expensive part is that your own delete statement turned out to be a suggestion. Notice how much rests on that one assumption. Your deletion endpoint, your data retention job, your right to be forgotten workflow, the quiet cleanup that trims a table every night, every one of them reports success the same way, in milliseconds, with the same untroubled green tick. You have built policy on a return code. The failure stays quiet by construction, so you lose an afternoon to it and learn nothing, keeping the same comfortable belief for months while the worse, the people who trust your answer have the least ability to check it, an auditor reading your policy, a user reading your privacy page, a colleague reading your runbook at 3 in the morning. Each inherits your confidence at face value. Your compliance story sits on the same crack. You have signed agreements that say deleted means removed, and you have a dashboard that says the delete succeeded. Both are accurate. Neither is evidence. Can you prove to an auditor that a row is gone rather than merely invisible? Hold that question. It is the one that costs you money and trust. So what is a tombstone? The term is worth pinning down, since it arrives in release notes undefined. A delete writes a record, and that record is called a tombstone, a small entry saying this key is dead as of this timestamp. It carries no row data whatsoever. In other words, it is 3 fields, a key, a marker, and a time, and the whole behavior that follows comes from those 3 fields being a write like any other. Think of it as a note pinned to a key rather than an eraser applied to a page. Analogy, tombstone is a wonderfully Gothic name for what that record really is, a boolean with a clock attached, and I would not trade it for anything more accurate. The surprising part is the size. A row you delete might be 200 bytes, the tombstone that hides it is perhaps 32, a key plus a 64-bit microsecond timestamp plus a type byte. So deleting data makes your dataset larger, by about 15% of what you removed, and it stays larger for at least 10 days. That is genuinely backwards, and it is the first sign that the word delete is doing something other than what it says. The initials that arrive beside this in release notes are worth expanding too. Log-structured merge tree is the design the term belongs to, and the middle word carries the weight. Note, what about the picture almost everyone carries? You imagine rows sitting somewhere on disk, and a delete traveling to that place and clearing them. Find the bytes, unset the bytes, move on. My own first attempt at explaining this used exactly that model. I said the engine overwrites the row in place and the tombstone is a receipt for the overwrite, which is wrong. But hang on, consider what that claim requires, a file being edited after it was written. The tidy version is easy to say and it survives about 4 minutes of contact with a real data file, since the file it claims to modify is physically never written twice. In other words, the eraser model does not simplify the truth, it inverts it. The definition to keep is the opposite one, nothing is removed, something is added, and what that means for every promise you make about deletion is the rest of this episode. So how does a write become a deletion? Start with what your storage engine holds. In a log-structured merge tree, the design underneath Cassandra, RocksDB, LevelDB, and most of what people now call a key-value store, writes land in memory in a sorted structure, and when that fills up the whole thing is flushed to disk as one sorted file. That file is never modified again. Not by you, not by the next write, not by anything. Because no file can be edited, the only way to reorganize anything is to read several files, merge them, and write a new one. That background process is called compaction, and it is the only janitor in the building. So ask the awkward question. Your row was written on Monday and sits in a file from Monday. On Friday you delete it. Where would the deletion go? It cannot go into Monday's file, because Monday's file is immutable. It goes where every other write goes, at the front, in memory, and then into a new file. Then the reader has to earn its answer. When you look up that key, the engine finds Monday's file holding the row and the newer file holding the tombstone, and it applies the only sane rule available, the highest timestamp wins. The tombstone is newer, so the answer is that the key does not exist. The row is still on disk, in full, readable, invisible because something newer says so. Not an erase. An argument between two timestamps. Why was it built this way? Patrick O'Neill and his co-authors published the log-structured merge tree in 1996 with one goal: turn random writes into sequential ones. A spinning disk then took a few hundred random writes a second and tens of thousands of sequential ones, so buying 2 orders of magnitude on writes was worth almost any read side cost. Deletion was collateral. Jeff Dean and Sanjay Gemawat then wrote LevelDB at Google from that same paper. Facebook forked it into RocksDB, and RocksDB now sits underneath a startling amount of what you run. The second mechanism is distribution. Suppose you have 3 replicas and one is rebooting when your delete lands. 2 process it. The third comes back holding the row, so 2 nodes have nothing and 1 node has data. Which is right? You cannot tell from the data alone, because absence carries no timestamp. Nothing is not a fact you can date. So the marker is how a distributed system remembers that it forgot something. It writes down that it forgot, in ink, with the time. Then the third replica hears the tombstone during repair, agrees the row is dead, and everyone matches. Which raises the next step: how long do you keep the marker? Forever is correct and unaffordable, because you would store a record of every row you ever deleted. Cassandra's process uses a grace window, 10 days by default, which is 864,000 seconds. Keep every tombstone at least that long, then let compaction drop it. Now you can name your own bug, so follow this arithmetic. First, a node goes down or unrepaired for longer than the grace window. Then the tombstone is collected everywhere else. That node still holds the row, so the next repair spreads it back as if it were new. 9 days. 10-day window. 1 replica behind. Your deleted row happens to be the freshest fact in the cluster. Case in point, here is the read amplification, and you can do it in your head. You store tasks in one partition and delete each one as it completes. After a busy morning you have processed 10,000 tasks, so that partition holds 10,000 tombstones and perhaps 5 live rows. Now ask for the live rows. The engine must scan every marker to establish those keys are dead. 10,000 examined, 5 returned. Double your throughput and you double the scan, because the work grows with rows you deleted, not rows you have. Cassandra warns you at 1,000 tombstones in a single read and refuses the query outright at 100,000, which is an admirable choice. Rather than serve a query that gets slower every day, it fails and makes you look. Those 2 numbers are not derived from anything. Somebody picked them because they felt right, and they have been the default for years. So how does compaction eventually clear the marker? It happens in stages, and the staging is why the delay surprises people. A tombstone written today lands in the newest file. Compaction picks up several files and writes one merged replacement, and only at that moment can it consider dropping anything. To drop your tombstone, it must be certain the merge covers every file that could still hold the original row, because a marker discarded while an older copy survives would resurrect that copy instantly. So the process waits for the grace window, then waits again for a compaction that happens to include the right files. 2 clocks, one you configure and one you do not, and the second is the reason a deletion you made this morning can still be occupying disk next week. In practice, a Bloom filter does not save you, and good engineers reach for it. Every log-structured merge engine keeps one beside each file, the structure Burton Bloom published in 1970, answering definitely not present or possibly present. So why does it not help? Your tombstone is present. The filter cannot skip a file that genuinely contains a key you asked about, so it says yes, correctly, 10,000 times. A structure designed to spare you work will confirm that all of the work is necessary. Sit with how perverse this next part is. It happens to be my favorite piece of unavoidable weirdness in storage. A marker exists since a system cannot represent gone by being gone. The only way a distributed store remembers that it forgot something is to write down that it forgot, in ink, with the time. Delete the memory of the deletion and the deletion itself unhappens. It should not work that way, and it cannot work any other way, which is a strange sentence to be able to say about a database. The honest trade-off is where the cost lands, and the Q table is the most reliably regretted schema in distributed databases. It looks perfect. Insert work, read work, delete work. Each operation is cheap, and the combination produces a partition whose read cost climbs with the number of items you have finished. Beyond a point, the design punishes you in proportion to how well it is working. There is a real fix: if you delete a contiguous range of keys, write one marker for the range instead of one per key. RocksDB calls this a range deletion, turning a million tombstones into a single record. In practice, how would you know any of this is true rather than take my word for it? You can check it yourself, and the honest test costs about 10 minutes. Run a single node of Cassandra locally, create a table, insert one row, delete it, force a flush, and dump the file with the tool that ships alongside it. You will see your key with a deletion marker and a timestamp, and the original row's data still sitting above it, which is the claim made concrete. Want the failure too? Set the grace window to a few seconds, delete a row while one replica is stopped, wait past the window, restart it and run a repair. Watch the row come back. The trade-off of doing this deliberately is an afternoon you chose, on a machine nobody depends on, instead of one that chose you. Nobody escapes this, and only the placement varies. Kafka, in a compacted topic, represents a delete as a message with a null value and keeps that marker 24 hours by default, so miss the window and your consumer never learns the key was removed. Elasticsearch marks a document deleted in a bitmap beside the segment and does not reclaim the space until segments merge. HBase writes explicit delete markers with the same timestamp rule. Amazon's Dynamo paper, in 2007, gave React the version that makes people wince: the deleted object cannot discard its causal history. Identical trade, for different invoices. Now the part where received wisdom is thin, and the honest answer is that I would rather say so than pretend. What should a grace window be? 10 days is a default, not a finding. The only principled statement anybody can make is that it cannot be shorter than the worst case time to repair every replica, and almost nobody measures that number, so the setting gets chosen by vibe and defended by inertia. Beyond that, the literature simply stops. I have never seen a convincing derivation of 10 days from anything, and if you know of one, I would like to read it. Caveat: the advice to prefer time to live expiry over explicit deletes is only half true. When a cell expires, it becomes a tombstone as well. You have not avoided the marker. You have moved the moment it is created out of your code, where you could see it, into the storage engine, where you cannot. So what do you actually do? 3 things, and the honest limit is that none of them is optional. Check today whether your repair interval is shorter than your grace window. If it cannot clear that bar, you have the resurrection bug right now and simply have not deleted the right row yet. Stop modeling anything Q-shaped as insert plus delete in one partition, since that shape does not survive its own success. And measure tombstone scan per read rather than disk usage, in practice the only number that warns you, because disk stays flat while the scan count climbs. Beyond those 3, everything else is tuning. In practice, none of this ever presents itself as a deletion problem, which is the caveat that makes it expensive. It presents as one query that used to be fast, or a replica falling behind, or an old record reappearing in a report while everybody assumes a colleague typed it back in. So what if the title of the incident never mentions storage at all? It will not. The word tombstone does not appear until the 5th hour, when somebody finally dumps a file and looks, and by then the trade-off has already been paid in meeting time. So, back to the question held open at the start. Why did that deleted row come back, and why did the database serve it without complaint? The delete was a write, that write had an expiry date, and one replica outlived the note saying the row was dead. Every component behaved correctly, which is the uncomfortable part. There is no misbehaving piece to fix. In practice, the system did exactly what it promised, and the promise did not include what anyone assumed. Which leaves a judgment I cannot make for you, and it is your call. Every system you will run has chosen where to put the cost of remembering what you removed, and not one of them made it free. You are not looking for the engine that deletes properly, because there is not one. You decide which invoice you can pay, and whether you are paying one you have never read. So ask yourself 2 things. When did every replica in your cluster last complete a full repair, and is that interval comfortably shorter than the window in which your tombstones expire? And if somebody asked you to prove a record is gone, what would you show them? The measurement is much cheaper than the apology.